All right, welcome everyone to today's Waterloo AI seminar. Just to lay down some ground rules for the talk, if you want, you can ask questions online as we go, either right here, raising your hand if you're here in person. If you're online, you can ask it either probably by, I guess, maybe asking the chat, and I'll relay any question in the chat. Yeah, today we're very, oh yeah, if you have any longer questions, maybe you can hold those till the end, where we should have some discussion time for going into more in-depth discussions. But without further ado, let me introduce our speaker today, Greg Yang. Greg is a researcher at Microsoft in Redmond. He did his bachelor's and master's at Harvard University in computer science and math, respectively. He's done some really amazing work. He's been recognized for his work so far in a number of ways, including the Hoops Prize for Best Undergrad Thesis at Harvard. He has also won he was the honorable mention for the very prestigious Morgan Award, which is the top prize for math undergrad in the whole world. So that's very impressive. He has also been an invited speaker at the International Congress of Maths for Chinese Mathematicians. And yeah, like I said, Greg comes from a background involving both math and CS. He's done degrees in both, and I think he blends this in a really beautiful way that I really appreciate. Some people, I think, manage to do important theoretical contributions. Some people manage to do very important empirical contributions. Greg, I think, managed to do things on both ends of the spectrum and connect them in very beautiful ways. He's done before some incredible work on adversarial examples, some of the, in my opinion, some of the best work in this area in the last couple of years, a very crowded area. So it's amazing that he managed to do such nice work there. And today he's going to be telling about part of his agenda the last couple of years involving something called tensor programs, which is a theoretical framework, but has also given rise to incredibly practical results, which he'll tell us about momentarily. So without further ado, go ahead, Greg. Thank you.
Thanks so much, Gautam, and everybody for having me here today. That was a very beautiful introduction. Thanks a lot. So yeah, let's just dive straight into the topic at hand today. So at face value, I'll tell you about how to tune GPT-3 on a single GPU via zero hyperparameter transfer. But there's a beautiful theoretical story behind all this as well, and we'll dive into this as we go. But to start, either as a practitioner or a researcher in machine learning, you often need to explore new ideas. And oftentimes, like you start small, right? You explore new ideas on small settings, small models, small data set. And if you're lucky, your idea works, and you get a really nice looking training curve that looks like this. But of course, the next step is to scale up, to go to the settings of your choice, and not too infrequently, actually, this will fail. And you get a bad looking curve like the orange one here. So at this point, you're wondering, okay, is it because like my idea sucks, or is it because just the hyperparameters are bad? I need to retune them. As this deep learning is kind of known to behave fragilely with hyperparameters. So this question is actually pretty easy to answer if you're doing things on a small scale. You can just retune the hyperparameters, But if you're talking about things like GPT-3 and like these large language models, each model takes a couple $1 million to train. You can't just do that every day, right? You have to be very careful about your choices. So this question of whether your idea works or not has this confounding factor of hyperparameters, and that's very hard to actually resolve when you're talking about these large models. So an example of what this work allows you to do is to automatically set those hyperparameters correctly and be able to get this nice looking curve if your idea actually is a good idea in the end. So it's able to resolve this uncertainty. The underlying technique is called maximal update parametrization, abbreviated as MUP. And in short, it's a principal way of scaling initialization and learning rate with the width of model. So I'll tell you more about exactly what this is in a second, but here's like a table encapsulating all the details I'll go into here. And you should just notice that in this table, we just specify how do you scale the different hyperparameters like initialization variance or learning rate for SGD or ATOM for different parameters of the neural network, input weights, output weights, hidden weights. But don't worry about details here. We're gonna come back to this later. But there's a key property of mu-p that we discovered and we're leveraging here. So this is what we call hyperparameter stability. So first, as a counterexample of the stability, let's consider, suppose you take a model in PyTorch in the default way of initializing and setting the learning rate. Then you can do the following experiment where you sweep the hyperparameters and plot the training performance on the y-axis, and you typically get a curve that looks like this, where there's like a maximizing hyperparameter that is right here, indicated by the dotted line. You can repeat this experiment for larger and larger models, and typically you get a set of curves that look like this, right? So here you see that the hyperparameters, best hyperparameters, are shifting as indicated by the shifting dotted lines. The curves are also crossing, like right here and right here, which means that like fixing the hyperparameter, you go up, you go larger, you actually do worse, right? So this is a counterexample, a bad example of hyperparameter stability. A positive example is with mu-p. So if you repeat the same experiments I described, but just with mu-p with that table I described earlier, again, like I haven't told you about the details of the table yet, but if you just follow the rules there, then you can see that the optimal hyperparameters are stable as you increase the width of the model, and the curves don't cross, which means that you always gain something when you increase the size of the model. So this is a cartoon, but on real settings, this actually is very close. So here I'm showing plots for transformer trained on Wikitext2 via Atom. So this is a pretty typical setting for language modeling. And on the left, again, you have kind of default, PyTorch style parametrization. On the right, you have mu-p. And again, you see the same thing here, where the curves are shifting to the left. So in particular, the best learning rate here, shifting to the left. And the curves are intersecting, right? So if you take the best learning rate for the smallest model and you use it on the largest model, which is indicated by this black dark curve here, then this might be an underlying explanation for this phenomenon here, where going larger actually did much worse, right? Because this learning rate, if you applied it for this curve, you're just gonna get really bad results. In contrast, if you look at mu-p on the right, the optimal learning rate is stable with the width model, and the curves are not crossing, so you always gain something when you increase the model size. So so far, we've been talking about this hyperparameter stability in terms of increasing width and looking at the learning rate, but this actually applies to very general hyperparameters, not just learning rate. So for example, here I'm showing you 4 sets of plots where the first is again learning rate, but the second one is cross-entropy temperature. It's like a multiplier on the output network. It's a different hyperparameter. Initialization standard deviation, which controls how large the model is initialization, the size of the weights are initialization, and also some learning rate schedules. So these are things like step decay, inverse square root decay, different learning rate schedules, right? Where we just kind of pick some of the most popular ones. And the point here is that when we look at all these different kind of hyperparameters, for the continuous hyperparameters, we see that the optimal values are stable with respect to the width of the model as you increase the width, which corresponds to the darkening colors here. And for learning rate schedule, which is a discrete property, you can observe that the ordering of the learning rate schedules are consistent as you increase the width of the model. So if the last one learning rate schedule is optimal for the smallest model, is also optimal for the largest model.
Sorry, Greg, one question. Can you make sure your sound is on, just in case someone wants to unmute themselves and ask a question?
My sound?
Yeah, your sound.
It should be on.
Yeah, I don't know if it's on or not, but just to make sure in case someone wants to unmute and ask a question.
Yeah, I think it's on.
Cool. Okay.
Okay. Okay. So yeah, so here I'm showing you, that like this stability property holds for many collections of hyperparameters when you increase the width of the model. And of course, the natural question to ask at this point is, okay, you can do width, can you do depth? Can you do other notions of model size or like the size of the training pipeline? So to answer that question, we just did like the very naive things of like just increase depth naively, don't do anything to adjust for it and see how stable we get. Versus like everything I've showed you so far comes from like theoretical motivation that I'll describe later. So like with everything has very beautiful theory behind it. What I'm about to show you next for depth and other things are just naive ways of evaluating whether naive scaling has already some stability. So again, here are the empirical results. So for empirically, when you scale depth in a pre-layer norm style transformer, you're gonna see that for the most part, like you have reasonable stability across depth. So here we're sweeping depth 2 to 32, and learning rate, cross entropy temperature, initialization, standard deviation, learning rate schedule, they're more or less stable. We're not saying this is the perfect solution here. We're saying what people are doing naively currently like looks reasonable, okay, compared to width where it doesn't look reasonable at all, what people are currently doing. And likewise, we also investigated batch size, sequence length, and training time. And again, for the most part, like things look relatively reasonable if you don't go crazy over the scale in which you sweep those things. So based on the theoretically motivated results on width and also the empirical results on depth and other dimensions, we propose this algorithm called mu transfer that allows us to, for the first time, tune extremely large neural networks that can be trained only for once. So instead of directly tuning it, you would shrink the model in along mu p and tune that small model and transfer the hyperparameters back to the large model. And by transferring here, I mean just like copying the hyperparameters, the best hyperparameters from the small model to the large model. And that's it. I mean, it's a very simple algorithm.
Right?
Yeah.
But as you were mentioning before, like, is this something about that certain hyperparameters being stable and other hyperparameters are not going to be stable, or?
So the plots I show you right now for visual purposes, I only sweep one hyperparameter at a time. But the result is more about like the entire collection of hyperparameters. It's a high dimensional space. Like that optimal value in a high dimensional space, like so learning rate, initialization, whatever, maybe even for every parameter, like individually for every parameter. So that high dimensional tuple is transferable across scale. Right? So we're doing all of that all at once. Yeah. Okay. So let me finally mention one property that I think is quite interesting, and you also have, I think, some implication of theory eventually. But so in MUP, there's a very interesting property. Actually, you probably would have taken for granted before, which is that when you increase the width of the model, the size of the model, the learning curves. So by which I mean, like if you plot training loss against training time, then the learning curves are always lower or improves throughout training as you increase the width of the model. So graphically, what that means is that the darker curves here, which corresponds to larger width, they always lie below the curves of lighter widths or lighter colors, and there's no crossing of curves, right? So this makes a lot of intuitive sense because you're putting more resources, you're burning more GPUs, if you increase the width of the model, so you better get something back in return, right? But this is actually not true for the current way that we're doing things. So in standard parametrization, if you use a small learning rate, you might get the illusion that this is happening for smaller width up to some point. So if you look at these curves, for example, but if you go even larger, you get a curve that just looks really bad and is worse than everything else. At this point, as an engineer, you would think probably okay, some floating point issue, some like probably some bugs in my implementation or something like that. But no, it's just like it's just a mathematical issue. Like just the math is incorrect. And it's even more obvious if you use a large running rate, in which case you just kind of, as you go wider, you do strictly worse, right? So you're putting more money in the system, but you're actually getting less bang for your buck. So that is to say that like what we should take for granted, which is that wider is better through our training, is only true for MUP and not for any other kind of parameterization. So everything I said so far, we carefully validated on models of increasing scale from MLP on CFAR10 all the way to GPT-3. So we're very confident that it's a very robust phenomenon, yeah, actually even across like modalities like language and vision. So to summarize, okay, why do we like MUP? One, it preserves hyperparameter optimal cross-model scale. This is theoretically guaranteed in a sense for width, and I'll dive into the reasoning in a couple sections. But empirically, for example, width 128 to 256 gives a good estimate of the optimal hyperparameter at low compute cost. And empirically, we verify this for depth and other things over reasonable ranges. So in particular, you can think of like estimating the optimal hyperparameter using a small neural network, kind of like estimating, the average height of Americans using 10,000 random calls to random Americans. Like the number of neurons is kind of like sample size, right? So we can use a small sample to estimate this kind of this property that is actually useful for much larger neural networks.
Can you remind what the with more commonly used in practices for these types of networks? Yeah, so like for GPT-3, for example, it's like on the order of thousands. Yeah. And how does the cost of training scale with the width? Yeah, so cost is roughly like proportional to the number of parameters. So I'll show this later, but like for example, on GPT-3, we transferred from a small model of 40 million parameters to a model of 6.7 billion parameters. So it's like more than 100 times increase. So it's a saving of more than 100 times at least, right? Okay. So that's one property that it has it affords hyperparameter transfer. Second property is that wider is better, right? So we always get some gain when we increase our resources. So altogether, this allowed this new technology called mu transfer or zero-shot hyperparameter transfer, where we can efficiently tune these really large neural networks, right? So it's efficient in both space and time. In space, because even if we need 1,000 GPUs to fit a GPT-3 or something on hardware, we can actually tune it in much less because we can shrink it so it fits on a single GPU, and then we can tune that single small model very, very fast, right? And we can parallelize it across a large cluster. So this is very, very efficient, and at this point, it's actually the only method for tuning large models. Like any other method is kind of just guessing. And we'll see like there's a large low-hanging fruit to pick just because people were guessing incorrectly. And by applying this method, we kind of just are able to pick that low-hanging fruit from the wrong guesses previously. Yeah, altogether, this enables more reliable scaling up on neural networks. Okay, so that's like a brief gist on what MUP is, mostly from an empirical perspective. The plan next is I'll tell you about what is MUP, then like some of the experimental results we have, and then some of the theoretical backgrounds for this, and I'll conclude. But I'll pause here for any questions here, either in person or in chat. Okay, great. So let's dive into some more details. So let me tell you actually what is MUP. So far I've kind of actually avoided that question, just telling you what you can do with it. So to give you the detail, it helps to motivate things with an example. So to start, let's think about a three-layer, multi-layer perceptron. So the equation looks like this, right? F as I is the output of neural network given input I, and the weights are
W1, W2, W3. And in standard parameterization, we would initialize the model as follows. So the input layer is sampled randomly with variance 1 over dn, where dn is the data dimension or the input dimension. And then W2 and W3 are the hidden and the output weights, and they're going to be sampled with variance 1 over n, where n is the width of the model. We're going to initialize the biases, B1 and B2 to 0, and we're going to denote the learning rate as eta. Okay, so if you use PyTorch, this should be like really natural to you. This is roughly what you're using by default in PyTorch. But if you were to do any of those experiments we saw before, where you sweep hyperparameters, say learning rate on the x-axis and different widths denoted by color here, you're going to see something like this, where the curves are crossing, right, and the optimal learning rate shifting to the left as you increase the model size. So it doesn't look very pretty. Now let's look at how MUP would try to fix the situation. So it essentially makes 3 changes in this example. So you can look at the color text. So one is the downscaling of the output initialization, output layer initialization. So the variance went from 1 over n to 1 over n squared. Second, the learning rate for the last layer is scaled down by a factor of n. Again, n is a width here. And finally, the learning rate for the input layer weight and the biases are upscaled by a factor of n. Okay, so at this point, you probably, if you've never seen this, you're probably thinking, okay, this looks like random changes. Why are we making these changes? I'll explain in a second, but if you just take this and run with it, you can see like a very nice set of plots in contrast with the left, where the optimal learning rate is stable and the curves are not crossing, right? So you always gain something when you increase the size of the model. Okay, now let's dive into some of the heuristics behind these modifications. So to tell you about these, it helps to first write out the output network, right? So the output network is like essentially a dot product between the last layer weights and the embedding. So I'm just going to write out this dot product. So this dot product, is the sum of n things. Again, n is width of the model, where each thing is a product of entry of the output layer weights and entry of the embedding here. Okay, so the first thing you can notice, maybe not very quickly, but you can definitely go back and just do some calculation yourself. But something you can notice is that every entry of this embedding actually has theta 1 size. So by theta 1 here, I mean that as the width become very, very large, like this entry, the typical size of this entry doesn't decay to 0 and doesn't blow up to infinity, right? So it's kind of like nice constant size object as your width becomes very, very large. Okay. So once you accept this,
only throughout initialization or throughout the procedure?
Throughout the raw training. Yeah, this is very important.
Okay.
Mm-hmm. Okay, so once you accept this, again, it's something you can just go back and do some calculation. You can actually make it easier for you by assuming like phi hyperbolic tangent or something like that. But once you accept this, then it's easy to see that these modifications ensure that the size of W3, each entry W3 has size 1 over n, right? So that means that as the width becomes large, the typical size of W3 scales inversely proportional to the width of the model. Okay, so why is this? Well, for example, this initialization, the variance being 1 over n squared means that the standard deviation 1 over n, which means that initialization, this is 1 over n sized. And the learning rate being an inverse, combined with the fact that this phi thing is theta 1, implies that the gradient of W3 is 1 over n. So we're not the gradient, but the update to W3 is size 1 over n. So over the course of training, this stays size 1 over n. Okay. All right. So why do we care that this output layer entry is 1 over n typical size? Well, you're summing up these n things, right? And each thing is 1 over n times 1 equals 1 over n sized. So you should expect that the sum is O1 at the very least. So that ensures that it doesn't blow up to infinity as the width becomes large. And you might shrink to zero. Like maybe there's some cancellation in the sum that causes it to go to zero. But the key insight here is that because you're training them, the W3 and this embedding actually become correlated over the course of training. So this actually, the correlation actually prevents any significant cancellation from happening in the sum. So that implies that in the sum you n things, each thing has size 1 over n. You don't expect a lot of cancellation. So the result is theta 1 size. Again, theta 1 here meaning as the width becomes large, you don't expect the output of the network to blow up or to shrink to zero. Okay, typically. This is important for many different reasons. Like just as a practical concern, you're implementing everything in hardware, and it has a floating point range that's fixed, right? If you eventually go to a floating point range because your model is too large, well, I mean that's pretty bad, because you're gonna waste like a lot of money just training your model and then boom, just get enhanced. But even before that, like just mathematically, the loss function you use has like a really fixed effective range. So for example, if your output is blowing up with the width model, then like if you square loss, that means that the gradient will also blow up as width become larger and larger, and this will cause like a feedback loop where you just diverge in your training. So that is just to say that like this condition on like the output being like theta 1 in terms of width is natural, and we should almost take it for granted. Like any reasonable way of parameterizing your model should satisfy this property. And what do you know, like the typical way we're doing things currently doesn't satisfy that property. So if you just remove these two changes and redo the calculation, you see that W3 has typical size theta 1, so that like the sum actually blows up like theta n. So it means like when the width is large, you expect the output to be proportional roughly to the width of the model. And it's something you can go back today and like verify this. Randomly initialize a PyTorch model, just play with it, and you can actually verify this.
So I guess the standard initialization tries to go for a different sort of normalization, sort of at a per neuron level, right? But you're maybe going for like the total output of the layer being normalized instead.
So the initialization actually is mostly fine. So the problem is two things. Like so what is the effect here, right? So like the modification first makes the last layer smaller initialization, and make sure that like the updates to it is also smaller. So conversely, the problem with the standard parameterization is that initialization is too large, and you're just updating it too aggressively. And so like if you just do things the typical way, just that output layer just kind of blow up. Like it's not even just kind of the body of the network isn't even at fault. It's just like the output layer is just too wild, too out of control. So you want to like kind of tamp it down a little bit. Yeah. Yeah. So layer norm is going to help a little bit. So layer norm ensures that in the 4 passes, right, like each neuron has like typical size of 1 or something like that, some constant size. But the problem with layer norm is that it doesn't guarantee, it still has an effect you have to deal with in the backward pass, right? So so imagine like the input to the layer norm is very large. Then when you calculate the gradient, it's like the gradient is inversely proportional to the size of the input, right? So I mean, one way you can think about it is like, like a layer norm is 0 homogeneous. So the derivative is -1 homogeneous. So like it's scale inversely proportional to the input to the layer norm. So if you don't handle the scaling of the object into the layer norm correctly, so let's say the input of the layer norm blows up with the width model, that means that in the backward pass, your gradient is going to be inversely proportional to the width of the model. So you're going to like cause just really bad conditioning on the gradient when you do backpropagation and you don't control the scaling behavior with width. So to summarize, like layer norm helps in the forward pass, but you still have problems with the backward pass. And as we'll see, like this is actually still very critical to fix in like BERT and GPT-3, which all have layer norms, right? So like we'll see that we're going to pick a lot of low-hanging fruit just from that. Okay, so that example, segues into this table you saw at the very beginning of the talk, which gives you kind of how do you a characterization of MUP in general. So again, what the table tells you is how do you scale the different hyperparameters of initialization, variance, and learning rate for HED or ATOM for different parameter tensors in your network. So input weights and biases, output weights, and hidden weights. And the way you read this table is black text plus the purple text gives you MUP, and black text plus the gray text gives you the standard parameterization or SP. So these color, where there's color, there's change. Now, if you look at the first two rows, that almost like essentially recapitulates what we saw in the example earlier, where if you look at here, the output weights, right? The variance we scale down from 1/n to 1/n squared, and learning rate for HED we scale from 1 to 1/n. Okay. Now, like in general, when we talk about like large scale neural networks, we typically are talking about transformers trained by ATOM these days. So like ATOM actually needs to be dealt with properly as well. So it turns out the right way to do this is to scale your output weights and hidden weights learning rate inversely proportional to the fan-in of that layer. Where here, just to clarify, fan-in means like the dimensionality of the input of that layer. Okay. And I want to emphasize here that I am like these expressions are expressions of how to scale. So it tells you that the like when you double the fan-in, you should have the learning rate, for example, but it doesn't tell you that you should use exactly 1/fan-in for your learning rate. Okay, it's an expression of how to scale, not expression of the exact hyperparameter you should use. This is very important because the actual hyperparameter should tune from the small model. And finally, like for transformers, there's another modification, which is that like from the original paper, like we calculate the tension logic as key times query divided by square root of dimension, where dimension d is the key or query dimension. But actually you should do k times q divided by d instead. And the reasoning is very similar to the example earlier, where like essentially during training k and q incurs correlation, so their dot product being a sum of d things actually will scale like d instead of square root d because there's not enough cancellation. Okay, so this is kind of a very brief overview, just like the first layer of the onion on what MUP is. I'll talk a bit more about like the theoretical underpinning here in a second, but any questions so far on this?
Maybe you'll talk about this later, but it just seems like this you're claiming a bunch of different rescalings which are appropriate. Maybe you'll talk about things besides hyperparameter transfer as well.
Yep.
Cool.
Yeah. Okay, so now let's go through some experiments. So in our work, we did a lot of experiments, but for purpose of time, we can't talk about everything. So here we're going to talk about 3 experiments. One is relatively smaller, so we can do more science, and then we're going to talk about actually large-scale models like BERT and GPT-3. So in this first experiment, we're going to explore the performance compute Pareto frontier. And this is done on IWST, which is a machine translation data set. And here we're going to transfer from a small model of 4 million parameters to a large model of 40 million parameters. So that's a 10 times increase. And this is this change in size is purely due to change in the width of the model. So again, when we change width, like everything has like very nice theoretical motivation and underpinning, and that we'll talk about in a bit. But we did many trials of random hyperparameter search to arrive at this Pareto plot, where on the x-axis you have a relative notion of compute, and on the y-axis you have eventual model quality measured by BOOST score. And the takeaway here is just that compared to the conventional approach, which is directly tuning the 40 million parameter model, ours, which involves tuning small 40 million parameter models and just copy the hyperparameters of the large model for seeing μp. Like these two curves has a difference in efficiency of 10 times about. So like, so in other words, if you look at any horizontal line here, the difference between the orange curve and the blue curve is about 10 times. Like the actually even better news is that as we scale up more and more from 40 million parameters to larger and larger models, like the efficiency gap actually only goes up because we can roughly still tune a fixed size model while the target model can grow kind of unboundedly in size, right? So here for science we can only do a smaller model, but when we go to BERT and GPT-3, like the efficiency gap is really more like 100 times or 1,000 times. All right, so now let's talk about BERT. So for BERT, we're tuning a small model of 10 million parameters and transferring to two models in the family, BERT family, so BERT base and BERT large. These are 100 million and 300 million parameters, roughly speaking. So what you can notice is one that we're tuning only once. We are tuning the 10 million model only once, and then the hyperparameters are automatically transferable to both BERT base and BERT large. Two, we're combining both theoretically motivated transfer across width with transfer across depth and training time, which are more empirical findings. So eventually the total tuning cost of the 10 million parameter model is equivalent to one full training run of BERT large. Right? So like at this point, like this is kind of quite small in terms of the cost. So on the right, I'm showing you the improvements. So okay, so the gist here is that like over a very strong baseline of like the best humans can do, or like human not knowing the right math can do by guessing hyperparameters, like taking that very strong baseline, we improve on that baseline by quite a bit across the board, and these are kind of just a summary of like what the improvements are in terms of either test loss or some like downstream tasks. But actually what I want us to focus on is that these improvements are actually larger for BERT large than BERT base. So BERT large is a 300 million parameter model and BERT base is a 100 million parameter model. So you can see that like the blue bar, the dark blue bar, which is BERT large, is typically much larger than the light blue, other than this MLI mismatch version. But in hindsight, this makes a lot of sense because, like I said before, people just don't really know how to relate hyperparameters to small models to large models. So people just been guessing, and their guess just are more and more wrong as the target model becomes larger and larger, because their guess is based on some models they can tune extensively, which has to be small by definition. So what this gap exposes is just that like the guesses are more and more wrong as the target model gets larger, and we're picking the low-hanging fruit of this wrongness, right?
Right.
Yeah.
For the third one, like for why the large one gets less.
Yeah, I think like there's a lot of noise in these kind of evaluations, so like I don't think you should read too much into this, especially like when I show you the GPT-3 experience, like a continuation of the trend. So yeah, so I don't. Yeah, like for these large model evaluations, typically a lot of noise. So you want to average over like many different tasks to get a like low noise estimate.
Can you remind what Megatron BERT is? Is this from the NVIDIA paper or something?
Yeah, so Megatron, so the original BERT is actually in hindsight like undertrained and undertuned. So Megatron was able to like, well, first of all, he ported in PyTorch and also like just training for longer and tune the hyperparameters better. So yeah, so it's a much better representation of the best baseline we have for human tuning than the original BERT. Okay, so finally on top of GPT-3. So So the setting here actually interesting, not just because of size, but also because when we collaborated with OpenAI, we don't actually get to see their code. So like everything is communicated up top. Like here's the mathematics, here's what we did on our side, and here's are some maybe tips and tricks.
By the way, one question from the chat. Just to clarify, is this pre-training or fine-tuning? Is this
pre-training? Everything I'm talking about is pre-training.
Yeah.
So yeah, in particular, just to clarify, like the main transfer here is about pre-training transfer, and then for these downstream tasks, we kind of just use standard methods, like no any new tricks here, just standard methods for fine-tuning, and that's what we get. Like we didn't tune any hyperparameters on fine-tuning.
Sure. So for you kind of just did the work beforehand, and then it gives you improvements automatically for all the downstream tasks.
Yeah.
Do you know, have you tried doing fine-tuning parameter transfer? Does that make a difference?
Yeah, so that's something that we haven't focused on. So there's various different reasons. One is just the cost of fine-tuning is much lower than for pre-training. So like the amount of money saved is much bigger for pre-training. Also, another thing is that depending on your downstream task data size, you might or might not be important to actually regularize properly. And regularization is something that we don't cover so far. I mean, like kind of for obvious reasons, like like MAA-P, as if you remember, the table it's a way of scaling your hyperparameters for the model size, right? But it doesn't know about the data size. But when you talk about regularization, it's really about like how do like the relative size of the data versus the model, right? So if you have a lot of data, you don't need regularization. If you have a very small amount of data compared to model size, you probably need some guidance or regularization, right, to get the right result. And the MAA-P, like you cannot expect to do that because you don't know about the data size. So just for that obvious reason, if regularization is the bottleneck, then we don't expect MAA-P to do very much, right?
I think there's one question which Jimmy wants to ask non-using himself maybe. So yeah, go ahead, Jimmy, if you're there.
Hi, Greg. This is really interesting. But the comment I want to make is that per downstream task pre-training is something that's very expensive that most academic researchers cannot afford to do, right? So we all start from BERT base uncased and do our fine-tuning down the road, right? So you're showing low-hanging fruit in specific tasks, but that requires pre-training an entire model just for that task. Do you have any comments about this?
So let me just clarify, right? So when we do pre-training on a single model, right, we're kind of doing a single pre-training for whatever task, like any number of tasks you want downstream. Once you have the model, you can fine-tune it on whatever task. So it's not the case that you have a new task at hand, you need to pre-train a new model, right? You don't need to pre-train a new model. You can just take an existing model and fine-tune it. Now, maybe the other point you're trying to make is that even for fine-tuning in academia is still rather expensive. Like if you take, I mean, maybe BERT is okay now, but I don't know, maybe like T5 large or something, maybe it's quite expensive to fine-tune. That like I can understand. And I think that just, okay, so there's two answers I have this. One is that we are actively working on a robust way of applying this to fine-tuning. But the other, maybe more something you can do today, more actionable, is that like you either have a lot of data or you don't have a lot of data for downstream tasks. If you have a lot of data, likely regularization isn't the bottleneck, then you can just apply MAA-P. And if you don't have a lot of data, then you can try multiple things anyway, right? Because you don't have a lot of, you don't train that much anyway. So you can probably just play around with a lot of regularization until you have the right result.
I guess this might be a clarification on your results though, right? So for example, in your diagram, your gain in QQP, right? Does that come at a cost in a decrease in performance across, other parts of glue or super glue or something like that? Or do you get uniform gains across all downstream tasks such that I can just start from a better backbone?
Yeah, the latter. So for BERT, we actually didn't evaluate over all of Google because I mean as the community understands right now, MLI and QQP are the two most representative tasks on Google, and everything else is kind of correlated with the performance on these. And also because we have the GPT-3 results where we did the extensive evaluation on few shot Google as well. And yeah, like so you can expect like across the board improvement.
Okay, great, thanks. That's exactly my question.
Yeah, great.
Yeah, just sort of to succinctly summarize it, you're getting a better pre-trained BERT large or whatever.
Yeah. Yeah, it's like a just a much better foundation model or foundation for whatever you want to do down. Right? You should generally expect like improvement in overall quality. Right. So for GPT-3 again, we didn't share code, right? So like they had to validate everything on their own code base and like understand the map themselves and to like implement everything correctly. So in that sense, you can think of everything I'm saying here as like independent validation of everything I've said before, right? So it's like a validation set. And indeed, they validated that hyperparameter optimum and stable for GPT-3 cross width, and wider is always better given the same hyperparameters. But now they just went quite crazy with the width to 33K. So then like we implemented everything and everything looks reasonable. Like we're confident that there's no bug. And we apply this to a 6.7 billion parameter version of GPT-3. And the transfer involves tuning on the 40 million parameter model and transferring to 6.7 billion. So again, that's a more than 100 times increase. And in summary, the total tuning compute budget is only 7% of the training budget, right? And this is just purely because like the model is the proxy model, small model is just so much smaller than the large model. And if you remember, like for BERT, the tuning budget was 100% of the training budget. And that's just because BERT is like 300 million parameters, so it's smaller. But the point here being that like as we go large, the target model becomes larger and larger, like the tuning budget becomes more and more negligible because just relatively the size of the small model compared to the large model is so much smaller. In summary, we beat the original GPT-3 6.7 billion parameter model over majority of metrics. So you can read this plot as some like representative tasks from the whole suite, but we actually redid all the entire suite of evaluations in the original GPT-3 paper. There's like a large table that you can read in paper. But more interestingly, like in line with the previous observation on BERT, that like on larger models we expect larger improvements. Like this new transfer 6.7b model actually is comparable. This is on par, not on par, with the original 13b model. So twice the parameter size, right? So that's a pretty big jump in quality. And again, like the larger the model is, the more we expect the gain to be. And this is not even the largest GPT-3 model. So like the largest is 175 billion, which is like 10 times larger than everything we're saying here. And you can imagine if we apply that, like the improvement is probably even more dramatic, but there's just a lot of resources, so we didn't actually do that experiment. But hopefully that gives you like the idea here of what the impact is.
Sorry, just as another clarification though. So you're doing hyperparameter search on 40 million and then scaling up to 6.7 billion, but you still need to run the 6.7 billion at least once.
Yep.
To actually do the pre-training, right?
Yep. Yep.
And then without actually doing HP search on the 6.7 billion, you actually don't know what the curve looks like and how much better you could be doing than blind guessing, right? But that's an experiment that's way too expensive.
No, so for 6.7 billion, we did everything, right? So there's the original model from the original GPT-3 paper. We also actually reran the original, like the models, to retrain the baseline using the original hyperparameters. And then we also applied new transfer to the 6.7 billion parameters. So we trained the 6.7b model like multiple times using different settings. everything there is like scientific. I was just saying the 6.7b model is not the largest model in the family, but we don't have like more resources to actually try doing things scientifically for the larger models. But at least like one takeaway here is that you can compare the 6.7b model we trained versus the original 13b model from the paper. We didn't retrain this, but if you compare the numbers here, they're comparable.
I see. Understood. Thank you.
Mm-hmm. So your question?
I was wondering if you have tried the new transfer from some vision-based transformer models to some other stuff.
Yeah. So in the paper we have actually let's see, for transfer. Okay. So yeah. So we applied in the paper. We applied to like ImageNet, like Redmond ImageNet. Privately, we also tried like vision transformer on ImageNet, I suppose, as well. Yeah, it just works. Yeah. Again, this is a very generic property, as we'll see from the theory in a second, that like it doesn't matter what the domain is, you know. Great. Okay, so let's talk a bit about the theoretical foundations. So first, let me pin down like what is the notion of parametrization we're talking about here. So this table you've seen a couple of times already. This tells you what μp is, and in general, you can think of a parametrization as just a way of filling that table, right? So like how do you scale the different hyperparameters with the size of the model, right, for different parameter tensors in the network? So parametrization is something like, you know, half the learning rate when the width doubles, but it's not something like, in this case, in our notion, it's not something that tells you use exactly learning rate 1 in -3 at width 1024, right? It's a coarser notion than that. It tells you how to scale when you have some existing hyperparameters. And geometrically, you can think of parametrizations as a set of coordinates or bases for the hyperparameter space. So here's a set of pictures that I think is, it's nothing like deep, but it sets your mind in the correct space so that we're on the same page. So as an example, starting with an example to illustrate this principle, consider different ways of initializing your neural network. So for example, like your weights can be randomly sampled from a Gaussian covariance STD squared, right? So you can draw a picture where like x-axis is the log STD, or y-axis is log width, and this particular way of sampling for fixed STD is corresponding to a ray that goes straight up, right? Indicating that like the variance is fixed even as you increase width. Now, like in machine learning, in deep learning, actually a more natural way of doing initialization is to sample like the variance or to set the variance as sigma squared over width, where sigma is kept fixed. And in this particular parameterization, you would have a ray that goes upward to the left, right? So in the sense that like as the width becomes larger and larger, like the variance actually decreases, so that you have this ray going to the left. Now the point here is that this is just our perspective of the space, but you can change coordinates and just look at the same space from a different perspective, and where you have like log sigma on the x-axis instead of log STD, then like this blue curve to the left actually now points up, and this green one now points to the right, right? Again, the point is that it's the same underlying space, we're just changing our perspective at looking at it, so it's change of coordinates.
So just to be clear, this is just a rescaling by the square root of the width or something?
Yeah, like, yeah, roughly speaking, right?
Okay.
And so the hyperparameter space has an intrinsic structure where each point it corresponds semantically to some computation procedure. In this case, the computation procedure is just the sampling initialization procedure given by either this or that. And a parameterization is an extrinsic set of coordinates on top of it, right? So I mean, if you know like manifold theory, this is kind of a very familiar notion here. Now, in general, like going away from that example, we're actually interested not in just one hyperparameter, but like a very like a bundle of hyperparameters which form a high-dimensional space. So in this cartoon, I'm gonna keep this cartoon the same graphical format, but now you should appreciate that like in the x-axis, even though it's array, it's actually now representing a high-dimensional space where, for example, this space consists of like initialization and learning rate for every parameter tensor in the network. And depending on your parameterization, on the left, I'm drawing the standard parameterization. On the right, I'm drawing the μp in this cartoon. Again, you can have different perspectives of this hyperparameter space as you vary with, right? Mentally, you should think of, again, these rays as lines in high-dimensional space. So again, the space here is high-dimensional, but the rays going up, they're gonna be rays still, and not higher dimensional. And again, like every point in the hyperparameter space specifies a training procedure that that spits out a training neural network, right? So like, for example, like this point could mean let's initialize all these parameters in this particular way and then train the parameter using these learning rates for 100 steps, so that gives you a training neural network, right? Okay, so accepting that, right? Every point it gives you a trained network, you can look at the isoloss contour surface. So like, if you're a guy, you can just do experiment training all the neural networks for every point in the space, and that should give you some kind of contour surface for how the loss looks like. And in particular, this is like very basic geometric intuition, but I just want to make sure that we understand this. A point in each space corresponds to a width and a hyperparameter choice. And the hyperparameter choice gamma is optimal for the width if and only if, right, like the horizontal hyperplane that passes through this point is tangent to the iso loss contour. Okay, this is just basic geometric intuition, but hopefully this is clear. As a counterexample, if you look at this point, the horizontal hyperplane is not tangent to this iso loss contour. As such, this is a suboptimal point. So this point is not optimal for this width, right? So this gamma is not optimal for this width, but this gamma is optimal for this width, right? So this geometric intuition is independent of the coordinates. Okay. Now let's put back the rays. Again, the rays here represent like a fixed set of hyperparameters as you increase width in a particular parameterization, right? So like the upward rays are like, you fix the hyperparameter in the parameterization that defines this picture here. So like this upper ray is fixed hyperparameter in μp because this perspective is μp, and from left is sp because the coordinates are in sp. But from observing like these cartoons, you can observe a couple of things, right? So one, on the right in μp, the optimal hyperparameter combination is stable as you increase the width of the model, which corresponds graphically to the fact that the points on this curve all have like horizontal planes that are tangent to the corresponding contour surfaces, right? And in addition, the ray is always traveling into regions of better loss. So wider is better. Right. So again, like these are the things that we actually talked about in the beginning of this talk as the properties that we like about μp. And this kind of puts a graphic a picture in your head for why that is. But in contrast, if you look at the left side, in SP, you can see that the optimal hyperparameter combination is typically unstable. So, like if you look at this curve, this line here, then really, except for this point here, every other point doesn't have a horizontal hyperplane that is tangent to the corresponding contour surface. And in addition, the wider is worse after some width, right? You can see that, like, as you travel upward, you're after this point, you're gonna just actually do worse as you go wider and wider. And this, again, corresponds to the earlier plots we saw where like going wider in standard parameterization actually does worse. So this, I think just in general, this is a kind of nice picture for like putting everything we saw earlier in context. Now we can think about, the infinite width limit. So what happens when you take the width to infinity? The limits correspond to essentially traveling along any of these rays, right, all the way to infinity. So for example, traveling along this ray gets you a speed limit, traveling on this ray gives you EP limit, and so on and so forth. You should expect to see continuation of this trend even at infinity. So like for the MEP limit, you should expect to see a loss curve that looks like this in the infinite width limit, where like this point is still optimal. And for SP limit, things are just gonna look bad in general. So to summarize, from that picture, you can see there's a kind of a trivial duality between parameterizations and infinite width limits, as in like each parameterization is exactly, in addition to being a set of coordinates, it tells you like how do you travel to infinity, right? And that defines the infinite width limit. And conversely, to define an infinite width limits, you need to specify how to travel to infinity, right? So so there's this duality between parameterizations and infinite width limits. Now this is kind of the key here, key thesis and concept underlying all of the things I've said so far, which is called optimal scaling thesis. So this relates what is an optimal parameterization and what is optimal limit. So if you just look at this picture here, like I said, there's a kind of trivial bijection between parameterizations and limits. And in this thesis, I'm saying something actually non-trivial here, which is that there's a connection between the optimal parameterization and the optimal limit. And you can notice on the left side, like the optimal parameterization is actually empirically useful, and what is optimal in limit is a theoretical object. And you have this rare kind of bridge in deep learning where you have kind of like a very tight connection between what is empirically very powerful and what is theoretically correct, I guess. So let me specify what I mean by optimal here. So on the left, a parameterization is optimal if it has two properties. So one, it has hyperparameter transfer, which means it preserves hyperparameter optimum across model sizes. Like has these curves that we saw many times already where the optimum is stable. Second property is that larger is better. So in other words, like if increasing the model size actually decreases performance, then you're not doing the right thing, right? So it's not optimal. So at least these are necessary properties in order for the parameterization to be optimal. But for now, I'm just going to define that to be the defining properties. Now on the right, I'm defining a limit to be optimal if it has maximal update, or in some colloquial sense, it means you maximize feature learning without blowing up. So at this point, probably, you feel like this is kind of a fuzzy notion. You don't really understand exactly what it means. That's expected. And like, as we talk about the width case, I think this will become more clear for you. But taking a step back, the point of this thesis is that, again, there's this tight coupling between what is optimal empirically. Like for example, having these two properties is actually very, very useful for scaling up your neural networks. So again, a tight coupling between what's empirically useful and what is theoretically useful and correct. And this is one of the, if you believe in this, this is one of the very few instances in deep learning where having a theoretical breakthrough kind of directly implies empirical breakthroughs, in the sense of like just better scaling for neural networks, better scaling laws, better capabilities for the bang for a buck. Yeah.
So when we talk about model sizes, you made it clear that they can be treated with that up.
Yeah. Yeah. So everything, most of the things we talk about in this talk has been focused on width. There's some discussion of depth and other things. So this thesis is formulated is actually like a thesis for any notion model size with depth, number of experts, and so on and so forth, or any combination of them. But in the second, I'll explain that this is true for width, and which is kind of exactly the reasoning that went behind this work. Like we had this like some primitive version of this idea, and then we knew we had the right limit, and which like led us to believe that we had the right parameterization, and that's what led to the work in terms of width. But like I said, in our work, we just naively tried things for depth and other things, and the optimal limit for that is still open. Like so this thesis is I think a blueprint for like figuring out the right to answer this question for depth and other notions of scale beyond width.
Just as a follow-up, is also when you say larger is better, based on an observation perspective, we don't have some observation to a lot of there has to be some notion that landscape and where the local are doesn't change too much, because then I could imagine that the changes are control.
Yeah. So yeah, from a traditional optimization perspective, yeah, you're perhaps like quite uncertain when the dimension becomes large, because you can have these, you know, like saddle points and stuff like that. In deep learning, I think I mean, surprising maybe a couple of years ago, but now kind of people kind of accepted it, is that like when you scale up things, optimization actually typically becomes easier if you scale it correctly, in a sense. And I think there are many approaches in trying to understand this phenomenon, like including, you know, like this new tangent kernel literature. But I would say that there isn't like very tight grip on understanding why that is the case. But kind of to go back on your question, I think in like just in the way today we understand deep learning, we can typically expect that like scaling up will always get you better performance, like faster optimization or something like that. Even with the possibility that there is setup points in this high dimensional landscape, but we kind of just somehow don't ever run into them.
Well, I mean, a simple counter example is you just take a fully connected network and increase the number of layers. Typically, beyond 2 or 3 layers.
Yeah. So you're absolutely correct, and that means that you're not using the optimal parameterization. Does that make sense? Okay. If you run into that, what you're saying, that means that you're not doing the right thing. And the point of this thesis is that like there should exist a parameterization by considering, you know, like maybe like a larger range of hyperparameters, larger range of architectures, and so on and so forth. There should be a parameterization that has its largest better property and also does better than what you're currently doing.
Okay, so yeah, because when people do that, they keep their hyperparameters the same.
Yeah.
And you're saying if we have your parameterization, you could keep the hyperparameters the same.
Yeah. Exactly. Great. So again, this thesis is formulated for any notion of model size, and as stated here, I think it forms a blueprint in understanding large-scale neural networks in the next couple of years. But this work is actually kind of a witness to the truth of this thesis for width. And here's a very visual example, illustration of this. So on the right, I'm showing kind of a 2D plane of parameterizations, which includes the PyTorch D4 and μ-p. And the x-axis is kind of a interpolation between PyTorch D4 and μ-p initialization scaling rules. And the y-axis is interpolating between their learning rate scaling rules. Okay, and on the left, we're plotting the kind of things we saw many times already, where different curves correspond to different widths. But like the way we're scaling the model corresponds to the point on the right, wherever it is at the current moment, right? And what you should take away from here is that only when this the green point is at mu p, is it the case that like, you know, the optimal hyperparameters are stable and like larger is better, and the curves don't intersect, which is kind of the same thing as larger is better. But for other parameterizations, like the curves are intersecting or like the optimum is moving away, so on and so forth, right? So again, like this illustrates that mu p is kind of like the unique parameterization that has these two properties, and I'll show you like why with the theoretical counterpart to this in a second, and like this is really the direction from right to left is really what motivated us to actually look in this area in the very beginning, because we believe we had the right limit, and so that implied that we have the right parameterization. Okay, any questions so far? All right, so I'm gonna prove this optimal scaling thesis for you for width. It's proving quotes because it's not purely mathematical. Only the first part is mathematical. So this is an argument that tries to classify all possible infinite width limits. And so this is just purely mathematical. And then the second part is a quote unquote physical argument, physical because we need to actually use some intuitions of what works and what doesn't work in machine learning. That's not like purely reducible to mathematics from first principles. But using these intuitions, we just eliminate all the limits and see that there's essentially only one that's ever reasonable, which is mu p. Okay, so for the mathematical argument, so this is called the dynamical dichotomy theorem, which is proved in the previous paper by me, but essentially it paints you a picture of what are the possible infinite width limits. Okay, and again, if you remember from the early discussion, like parameterizations are essentially the same as limits. So it's also a classification of the parameterizations of large width neural networks. And so the basic picture looks like this. So most of the parameterizations or limits are not interesting in the sense that they're unstable or trivial, i.e. training blows up or training gets stuck in translation in the limit. So it's a sea of garbage, but in the sea of garbage, there's like an island that's actually more interesting. So within the island, most of the parameterization limits are in this kernel regime, which means that like the function evolution in the infinite width limit is described by a functional equation for some kernel k, like so. So in other words, like the change in the function is proportional to the kernel k times the loss derivative of the function. Okay, so everything in this region can be described using this kind of function. So if you know a bit more of neural network theory, the neural tangent kernel limit is a particular vertex in this region. And then the standard parameterization with constant learning rate, like we saw earlier, is something that blows up. So it's unstable in the large width limit, but you can use a small learning rate, like 1/width, in which case it's stable and non-trivial, but it falls in this kernel regime. Okay, so actually there's something even more interesting, which is the codimension 1 subspace of this island. So if you look at these two brown lines, they correspond to like two facets of this polyhedron in the high dimensional space. And in the subspace, you have feature learning. So like the representation of the models will kind of change over the course of training. The property that I want to focus on here, which will be useful and we'll come back to in a second, is that this space, this brown plus black point here has a symbol structure. There's a maximal limit, so which is the mu p limit, and everything else is non-maximal. And what that means is that like any point on the brown line here can be understood as some kind of parameterization or limit that looks like this. So for example, you can take mu p and you can modify to make a new parameterization by, like, say, lowering the learning rate for the first layer by a factor of width, right? Then when you take the infinite width limit, that effectively means that the learning rate for the first layer is effectively 0. And so this is an example that where this thing I'm talking about here is that, like, this is the only kind of non-maximal feature learning limit that can occur. So any non-maximal parameterization limit essentially just differs from mu p by, like, just like not really learning some specific parameter, biases or input layer or some hidden layer, for example. And mu p is the only one that kind of does feature learning and learn as much as possible for all the parameters in the model. Okay, so we have to, so this will actually come out to be important later on, but this is kind of like the structure theorem or the classification of all possible limits, infinite width limits on neural networks. Okay, now we come to the physical argument. Again, we're going to need to use some intuitions of, like, what works and what doesn't work in machine learning. But here we're just going to go through all of the parameterization here and see, what makes sense and what doesn't make sense. Like, essentially, like, which ones are possible to satisfy these two properties, hyperparameter transfer and larger is better, right? So first, we can look at the unstable trivial ones. I mean, this is easy. Like, we can eliminate it from the get-go because, in these ones, the optimal learning rate will converge to 0 or diverge, right? So they're just not good ones to look at. Second, we can look at the ones in the kernel regime, which is, like, in this the bulk of this polygon. Again, there are multiple reasons to reject this, but concretely, like, we actually know that from various experiments in the past, that the kernel limits just actually underperform the finite neural networks. So, like, this is a particular, like, set of numbers for like, kernels and neural networks, and the fact that it underperforms finite neural networks means that you can't have this larger is better property, right? So that's also something we can eliminate. Then we have the feature learning regime. So if you recall from earlier, right, like I said, there's a simple structure in this region. So if you're not mu p in this region, then you must differ from mu p by essentially lowering the learning rate or something, so that, like, in the limit, that learning rate is effectively 0. It's like, say that the input layer is not learned in the infinite width limit. But that essentially means that you cannot satisfy the hyperparameter transfer property for that particular learning rate, right? Because, like, that learning rate has non-trivial effect for finite neural networks, but then you essentially set it to 0 in the infinite width limit, so it has no effect. So there's no way you can transfer the optimal value for that learning rate. So, like, we essentially then have eliminated everything in the space except for mu p. Like, mu p is the only thing that possibly can satisfy these two properties. And like, I think from the heuristic mathematics we did in, like, making sure that the output doesn't blow up and so on and so forth, like, you actually already kind of suspect these two properties are true, and then it just comes to verifying that empirically this is indeed the case. Okay, sounds good. So hopefully I convince you that auto-scaling thesis is correct for width. Great.
Yes,
Okay.
there's about 10 minutes left. So,
yeah, I'm like at the end here. Let me just say briefly, like, a couple words about tensor programs, because this is kind of the underlying technique of everything we said so far. Just briefly, like, tensor program is essentially a computation that's composed of matrix multiplication, quantum-wide nonlinearity, but just, like, the composition is in a very structured way. And, like, the first key insight, which I'll call the Church-Turing thesis for deep learning, is that any deep learning computation can be expressed as tensor program. I mean, as written here, it's almost like trivial, because, I mean, deep learning, deep neural networks is just map modes and nonlinearities. I mean, like, what else is it, right? But what's non-trivial is that the following is also true. If you are able to write things in tensor program, which again, I kind of hidden away details of what the program actually is, but there's like some rules to follow. So if you are able to write out some computation for in this form, then you can prove a theorem that says that like that tells you how to calculate the infinite width limit of such a computation. So in particular, if you write out maybe like in the next slide I'll show you this, but yeah, if you just write out all of like the SGD, the computation graph of SGD, so you're unrolling SGD here to a giant computation graph. This theorem allows you to take this complicated computation graph to infinite width limit, and that gives you kind of the feature learning limit with the mu limit. Whereas like prior works are mostly kind of like stuck initialization, like they're essentially either taking the first limit of first forward pass or limit of first backward pass. Like they're very careful not to venture out of the initialization region. Whereas because we can like kind of take the limit of any computation graph, we can like venture very far away from the initialization. And so one way you can think about like this this master theorem here is that AutoGrad, it's kind of calculating the gradients for any computation graph, and master theorem is kind of doing the same thing for infinite width limits. Yeah, so I'll just put this one slide here on like the tensor program series of papers so far. So the work I'm describing here is TP5, but I started working on this thing like second half of 2018, and it's been a kind of a long journey in a sense, but also quick in the sense that it's actually pretty rare to see like very deep theoretical like work kind of surface into like $1 million impact very quickly. But yeah, in that sense, this is kind of rather quick. And I think that the point in this slide, I think, is just to encourage like the younger folks in the audience that you can try to have long visions and execute on them. And there's actually a lot of low-hanging fruit from the typical researcher is mostly kind of nibbling at the edge of what's known, but if you can like have vision and dig deep, you can actually do a lot of things. And like the practical uses of like this series is pretty much zero until the very end, in which kind of it's quite quite useful. But the point is that you have to have a vision and follow that vision. Okay, so I'll say a few words on conclusion. So the Manhattan Project and space program, they're well-known achievements of humankind in the 20th century. But scientifically, actually, the commonality is that each empirical test is very expensive. So they require extensive theoretical calculation first before launching any empirical test, right? So, and I will argue that today with large foundation models in language of vision, we're in a similar territory here because training these large models is quite expensive and requires a lot of preparation, and doing so reliably and optimally is by no means a trivial thing, right? And it's a very actually difficult problem to answer in general. And as such, like theory can actually play a very crucial role here, just as theory played a crucial role in both Manhattan Project and space program. The planning trajectory, like your space shuttle to Mars if you don't know gravity. In general, like you can think about the economy of insights at scale. So we can compare the stereotypical theoretical insight versus the empirical insight here. So when the problem scale is large, empirical insight is very expensive, but when the problem scale is small, the empirical insight is cheap because again, you have to do experiments, and the cost of experiments is proportional to the problem scale. But in the pure setting, like theoretical insight, you just need to eat and sleep and coffee, whatever, right? It's a very basic requirements. And like Einstein didn't need GPUs to discover general relativity. So the theoretical insights in its purest form is constant in cost in terms of problem scale. So on small problems, on CVAR 10 or so, like empirical insights are always going to have a better edge. But on these like large problems, like large scale pre-training, these are going to be actually quite crucial. Yeah, let me describe this. Yeah, so I like this analogy with statistical mechanics and chemistry of this notion of intensive versus extensive properties. So yeah, intensive means something that doesn't depend on the size. So like the melting point, boiling point of a jar of liquid, color, density, viscosity, and so on and so forth. Whereas extensive means depends on the size of mass, the systems like mass, volume, entropy, and so on and so forth. And like in analogy with that, but in neural networks, we can also define intensive and extensive properties. So extensive, are things like loss, accuracy, which as we see in today's neural networks, they're still kind of improving with size as we speak. We also have these emergent phenomena like few-shot and context reasoning in language models or artistic image generation that comes with the size of the model. In contrast, intensive are things that converge very fast with the model size. So like optimal hyperparameters in UP, like in this talk we described, maybe some scaling loss. But in general, I think a very interesting question is that what are other intensive properties of neural networks that can be used to predict behavior of large neural networks from small ones? Particularly like an interesting thing here is that if you don't know MIP, the optimal hyperparameters actually seems like they're extensive properties. Like you can't actually predict them very well with the size. But if you switch your perspective, right, change your coordinates from SP to MIP, then all of a sudden this extensive property becomes intensive. And I think it's a very tantalizing possibility for all these other behaviors on the right that we care to know in these about these large models, but currently it's hard to predict. So yeah, finally, I like to make this another analogy, which is that there are 4 fundamental forces in physics as we understand it currently: gravity, EM, weak nuclear, strong nuclear force. Standard model has been like very successful at predicting these 3 forces in smaller scale systems, and relatively has been successful at predicting gravity in large scale systems. But we're still looking for that theory, everything that bridges this gap, right, in between these 2 things. In large scale deep learning, we also have fundamental forces with depth, training time, so on and so forth. Like these are the compute hyperparameters that you scale when you try to scale up your neural network or training pipeline. And in a sense, we understand with rather well, maybe not completely, but like rather well, in part due to tensor programs. But we have much less understanding of these scaling dimensions, and it's not even clear that they're fundamental scaling dimensions like we understand in physics. So I think the holy grail in this area is a theory of everything for large-scale deep learning. And I see optimal scaling thesis as a blueprint for trying to arrive at this. So if you recall, right, like this thesis posits a tight connection between the optimal parametrization and the optimal limit. And for the width of case, with the case of width, we essentially did the following. We took all possible infinite width size limits and we classify all of them. And then there's only one that makes sense. So then we posit that gives the optimal parametrization, and we profit from that. And I would say I would posit that this is the roadmap we should also take for these other notions of scale and actually in conjunction with each other. And if you look at this, like taking limits and classifying objects are things that mathematics actually is very good at. It has many successful stories on those fronts. So this is an area where, like again, like theorists and mathematicians have a lot of leverage, but it's really underutilized at the moment because for various reasons people are not thinking about these. Okay, so I'll end here. Here's the paper with the QR code you can scan, and you can use the MUP today in your PyTorch code today via pip install MUP. Thanks.
Yeah, thanks a lot, Greg.
Yes.
So, something that, to the extent that I understand these things, so to the extent that I understand the neural tangent kernel, you take like infinite limit on the size of the machine, not on the number of candidates.
Yeah.
So, but then you said in your talk that the regularization parameter, you need to compare the number of training instances to the size of the machine. So you couldn't do that for the neural tangent kernel because the one is going to infinity is.
So yeah, one insight of neural tangent kernel is kind of like when you take the width to infinity, you don't actually get like something like, because it converges to kernel, right? So something's pulling it back from like just overfitting everything, right? So it's not like, you know, if you let width go to infinity, you will overfit more and more, right? So there's like a bound to it. It may, so like the performance actually, you should expect the curve. If you're in the neural tangent kernel parametrization, you should think of like the test loss as something that maybe like decreases up to some point and increases again, and then flattens out. It's never gonna like, you know, the test loss is never gonna like go up unboundedly, but it's gonna just like, you know, like plateau at some point. But there's like gonna be a dip where like the optimal loss is like some width where there's optimal loss. So this is less true for the feature learning limit. Like we don't have something natural that's holding it back, but there is a limit, like in the sense that like, again, you're not gonna kind of overfit wildly. It's not like the test accuracy is gonna drop to 0 as you get larger and larger. It's gonna just like, you know, flatten out at some point. And depending on the situation, the data set, you know, like this, the infinite width limit can be either like requires a lot of regularization or it requires only a little bit of regularization. So it depends. Like I think for like there's certain settings like, you know, some like 2-layer neural networks with, you know, Gaussian data or something that, you know, you can characterize like what is regularization you need. But, you know, if you're talking about like modern day transformers GPT-3, like, you know, like I mean, other than like sensory tensor programs, other theories kind of don't scale very well with like, you know, architectures or training paradigms. But yeah, I think in the future, you know, this is something we're thinking actively, you know, like how do you think about regularization in general? Can we piggyback on the tensor programs framework to be able to deliver some insight for any situation that you can run into in PyTorch, for example? I think, yeah, again, like that's a very exciting question, and that's a very big question as well. Mm-hmm.
We're a bit over, so maybe we should take, like, if anyone else has questions they want to ask Greg, we can sort of take it offline. But let's thank Greg one more time, and yeah.
Well, thanks.